Oh, what's up, everybody? Mr. Kozad back with another video lesson. Today's topic is a calculus lesson, and it's on finding the area. Sorry, squeaky chair, goodness. Find the area between two curves. This is part one of a two-part lesson. So there's a second video that you can actually go find right now if we're going through this video and it's too easy for you. Maybe check out part two where we talk about doing this using technology. But today we're going to do it all by hand. We're not going to use any sort of technology to help us do that. So before we get going, I got to tell you, today's a great day to be alive. I hope you're excited. I hope you're with it. We got a lot to do today. Get a paper, get something to write with, and let's get started. So some notes before we actually do some problems. Okay, basically when you find the area between two curves, we're going to start by drawing a graph. We're going to graph multiple curves on the same graph, and we're going to find this section of the graph that's enclosed by all of these different lines, okay? It'd be pretty easy once you actually see the graphs. But once we get the graph, the calculus that we're going to use, and I want you to write this down, is we're going to take the integral of the top curve minus the bottom curve. Top curve minus bottom curve. That might not make a ton of sense to you right now, but it will as soon as we're done with this lesson. And we're going to have a right bound here and a left bound here, or right slash upper, left slash lower, okay, is how those would be referenced, okay? So this will make a ton more sense as we jump in and start doing some problems. So here's number one. It says find the area enclosed by the two curves. So our two functions here, f of x equals x, and g of x equals the square root of x. So the first thing that we have to do here is actually just draw a sketch of the graph. Okay, the line f of x equals x is a linear function that passes through the origin, slope of 1, looks like this. And square root of x, we all know that graph. Now what you might not know, oh goodness, where am I? Oh geez, okay, here we are. So what you might not know here is that we, let me fix this here. Lost my train of thought. Can't trust technology, okay? So on this graph, the square root of x, what's actually going to happen here is this graph's going to come up above the line y equals x and then flatten itself out. So when you see it like this, okay, you can see that that's probably not a good color. Let's do green. You can see that this overlapping shaded region, there's this little section right here that's enclosed. Okay, this little green section is enclosed. So that's what we're going to find the area of. Okay, so we need to find two things first. We need to find where does that start and where does it stop. Okay, now the best way to find those intersection points is we use some basic algebra 2, where we set those two functions equal to each other. So x equals the square root of x. So when I do that, I get x squared equals x. Subtract x on both sides, you get x squared minus x equals 0. Factor in x out, you get x times x minus 1 equals 0. So you get x equals 0 and x equals 1 as our intersection points, which makes sense. We can clearly see that this is x equals 0, which means that this point here would be x equals 1. Okay, hardest part's over. Now we do the calculus, okay? So the calculus tells us to take the integral of the left, and let's get our bounds. So our left bound or our lower bound is 0. Our upper bound is 2, because look, 0 is where the enclosed shaded region starts, 2 is where it ends. So we go from 0 to 2. Now that equation I just had you write down was top curve minus bottom curve. What that means is you look at this section and you decide, I don't want to color that, I want the laser. You look at this section, okay, and you decide what curve is on the top and then what curve is on the bottom. Well, the curve that's on the top is the square root of x. And then we subtract the curve that's on the bottom, which is y equals x. And we integrate this with respect to x. So this is a pretty easy integral, okay? We end up getting 2/3 x to the 3/2 power minus 1/2 x squared, and we're evaluating that from 0 to 2. So at this point in our relationship together, you should know how to evaluate an equation like this. You plug 2 in for x and see what you get, and then you subtract what you get when you plug 0 in. Now plugging 0 in here is super, super easy and convenient. Not much work involved. That's just going to be 0. So the answer to this is really just going to be whatever we get when we plug a 2 in for... Oh my gosh, you guys probably all already realized this. Cosette, why did you write a 2 there? That was my mistake. It should be a 1. Yeah, somebody probably noticed when I wrote that upper bound originally that it was supposed to be a 2. Or I'm sorry, it was supposed to be a 1 and Cosette wrote a 2. I wish I could say I just did that to see if you're paying attention, but it's a mistake, y'all. Even the best, even the great ones make a mistake. But we're going to keep rolling because it's nice to know that even people like me are human. So here we go. So now that that's fixed, okay, it doesn't change anything with the derivative or the integral. So then we plug a 1 in, and when we do that, we end up getting 1/6, and that's square units since we're talking about area, okay? So the area of that little green sliver there is 1/6 square units. Let's rid ourselves of this problem. Sorry I messed up on that. Okay, here we go. Number 2, find the area enclosed by these two curves. So now we have x squared minus 1 and negative x plus 1. So first step, draw a graph of both curves. So x squared minus 1 is a parabola that's shifted down by 1 unit. Negative x plus 1 is a line that passes through quadrants 2 and 4 and looks like this. So our intersecting region here, or our shaded region, is this section right here. So this is the area that we're going to try to find the area of. So I need to find, obviously, the bounds. So I need to find those two intersection points. Again, the best way to do this is using some simple algebra 1. This might be closer to algebra 2. Okay, x squared minus 1 equals negative x plus 1. So we end up getting x squared plus x minus 2 equals 0. That trinomial factors to x plus 2 times x minus 1. Set each one of those equal to 0, and we get x equals negative 2, and we get x equals 1 as our two x values. So clearly, we see that this is probably going to be x equals 1, and this is going to be x equals negative 2. So now we're ready to actually build the integral. Okay, so the integral from lower bound is negative 2 to upper bound is 1. I'm not going to mess up that upper bound again, just like I did on the last one. Geez, I can't let that go. Okay, top curve minus bottom curve. So look at the shaded region. Top curve is the negative x plus 1, so that's the one you're going to write first. Now, I like to group that in parentheses just so it reminds me that it's all one function, and that's really important when we subtract the bottom curve. Now, the bottom curve very clearly is the quadratic, x squared minus 1. And it's really important to leave that in parentheses because if you don't, you're going to forget to distribute the minus sign to both parts of that function. So it's really, really important here that you put parentheses around that function, especially if there's more than one term, okay? So evaluating this integral is pretty easy, okay? We've got negative 1/2 x squared plus x minus 1/3 x cubed plus x. And we're evaluating that from negative 2 to 1. I will let you plug and chug that. You plug 1 in for every x that you see and get a number, and then you plug negative 2 in for every x you see and get a number, and do that subtraction, and you end up getting 9/2 square units. Okay? Number 3, next problem. Same directions, different functions. So here we have f of x equals negative x, and we have g of x equals x cubed. Oh, and they add a third. We have x equals 2. Okay, so this graph is going to have 3 lines on it. It's going to have 3 lines. Okay, so I've got my x and my y-axis. I've got the line negative x. Looks like this. The cubic function, x to the cube, comes through here, and it's got this really cool little snake through the origin. It looks something like that. And then the line x equals 2 is going to come somewhere over here, and it's going to look something like that. So our little section here is this triangle-ish piece. It's not a perfect triangle because the side here is curved, but that's our area there. All right, now finding the upper and lower bound is actually pretty easy. We don't have to do much work on this because we can see its lower bound is 0, and the upper bound here, that x value, is defined for us as 2. Okay, so those are our bounds. We're going to go from 0 to 2. Okay, now from 0 to 2, we got to figure out what curve comes on top. Okay, so the curve that's on top is this one right here. And if you remember, that's the cubic function, so that's going to be x cubed minus the curve on the bottom, which is negative x. So it's important, again, to make sure that you put that negative x in parentheses, because then you'll see to distribute that negative sign. Okay, so evaluating this integral is not that bad. We get 1/4 x to the 4th plus 1/2 x squared evaluated from 0 to 2. So again, I'll let you plug and chug. You plug a 2 in for x, see what you get a number, and then you subtract what you get when you plug 0 in for x in each one of those functions. Clean that up, and when you're done, you should end up getting 6 square units. 6 units squared. So the area of that little section here is 6. Okay, hopefully you're finding these to be pretty straightforward and pretty easy. We're going to keep going. We got one more problem left together, and then we are done for the day. Okay, so here we go. Find the area enclosed by the two curves. We've got, actually, it's 3 curves here. So let's see what this graph looks like. So we've got, get this. Okay, we've got 2x squared. I like that one. It's an easy graph to draw. 2x squared looks like this. We've got the line y equals 8, so something up here. Ooh, and then we got the line x equals 0. Okay, so now this is kind of interesting because you could be looking at this and you might be thinking, well, Kozad, we can actually, there's which section is it? Okay, could it be are there 2 possible sections here? And I think that yes, actually there are 2 possible sections here, and I'm going to show you. If you don't see the 2, you're like, what are you talking about? There's only 1. Okay, you could argue that this is the section that's enclosed by those lines, and you would be right. Okay, that's totally fine. But somebody else could look and say, well, no, this is the section that's enclosed by all of those lines. And you could actually also be right. Okay, so what we're going to do here is we're going to actually evaluate this 2 different ways. So there's 2 different ways we can do this. We're going to have so much fun with this. I need to give myself a little bit more room, I think, over here. Okay, so we're going to do this 2 different ways. Okay, 2 different ways. All right, first way is pretty easy, honestly. We've got the integral. Lower bound starts at 0. And then we got to figure out, what is this point up here? Okay, well, I know that the y value is 8 at that point. So I've got to figure out, okay, when y equals 8, what does x equal? So I'm going to write myself a little equation. 8 equals 2x squared. That's what I want to figure out, is where does 8 equal 2x squared? So divide both sides by 2, you get 4 equals x squared, and then you see pretty clearly that x equals plus or minus 2. So the coordinate of this point here is going to be 2, 8. Okay, so my upper bound is 2. Top curve minus bottom curve. Now be careful on this. The top curve is a horizontal line, y equals 8. So that function is just an 8. Minus the bottom curve is 2x squared. And we're using x. So this integral is 8x minus 2 times 1/3 x cubed. And that's evaluated from 0 to 2. I'll let you do the heavy lifting on that and plug and chug. Plug a 2 in for each x and see what you get. You don't have to plug a 0 in for each x because you know that when you plug a 0 in, that you're going to end up just getting 0. So when we do that, we get 32 thirds units squared. 32 thirds units squared. Now, if you're one of the people that when you graphed this, you saw the second side as what's shaded, the work's going to be very similar to this. The only thing that changes is our upper and lower bounds, okay? Our upper and lower bounds are changing here. So we've got -2 to 8. So -2 to 0 is going to be the bounds that I use if, again, this is only if you saw this section as being the shaded section, okay? Top curve is still 8. Bottom curve is still 2x squared. We're using x as our variable. So this derivative is 8x minus 2 times 1/3 x cubed, exact same as what we had on the last scenario. But this time, instead of evaluating from 0 to 2, we're going from -2 to 0. So again, I'll let you plug and chug and see what you get. Should not be surprised, especially you that are savvy. You should see that we actually get the exact same area, which we should not be surprised because those two sections are symmetrical across the y-axis. So if the area, we shouldn't be surprised that this area is the same as this one. 32 thirds units squared. So my people, that is your very first lesson on finding the area between two curves using calculus and integrals. Make sure you come back and watch part 2, which is where we start to look at some more interesting types of functions, but you get to use your calculator or graphing technology to be able to help you do some of the heavy lifting on that. So hopefully you liked this. Hopefully it was helpful. Let me know if it was great. Let me know if it was terrible. I appreciate you guys, and we'll see you next time.